Alright, so let's start the 9th chapter, continuous functions on R. We of course know what a function is, and now our focus is going to be this type of functions. A function whose domain D is a subset of the set of real numbers and whose range is the set of real numbers. In fact, we have actually already done so for a specific D, namely the set of all natural numbers. That is, we have already considered such functions, and these functions are, if you recall, nothing but sequences of real numbers. For example, if you call the image of this natural number n under f an, then this function in fact is nothing but this sequence of real numbers. This we have studied extensively. We have seen what we have seen the notions of convergent sequence, divergent sequence, and convergence means there is a limit. Now we are going to do a similar thing for some other types of sets D. Okay, for such functions also we are going to have a notion of limits, and closely related to that notion is the concept of continuous functions. Now the type of subsets that we will be considering here primarily are the intervals. Okay, so that's how this section basically starts. We have, of course, besides intervals, there are other sets also that we will consider in place of domain, of any function, but intervals are the main focus. So let us start with the definition of intervals itself. So this is definition 911, and it has this name also. Intervals. What we are going to now do is that we will define intervals fine, but not just in R, since we have the slightly larger system of extended real numbers, right? If you recall, this is just the system of real numbers along with these two extra symbols, minus infinity and plus infinity. In fact, in this extended system, we have the order relation, which is an extension of the ordinary order relation on R, and it has all the properties that the ordinary order relation has. So using these facts, we are now going to define intervals not just in R but actually in R star. So let A and B be elements in R star, that is, let A and B be extended real numbers. We define the closed interval denoted by this symbol a comma b within square brackets as this. It is defined to be the set of all extended real numbers x such that a is less than or equal to x and x is less than or equal to b. See the inequalities here. In both the inequalities we have the option of equality. Okay, and keep in mind that this a and b may be plus or minus infinity, this x also may be plus or minus infinity, right? So that's why this interval is, in general, you can see from the definition itself, a subset of R star, a subset of the extended real number system. And there are three other types of intervals also. Let's continue this. The half open intervals this and this as this is the set of all extended real numbers x such that a is strictly less than x and x is less than or equal to b. And similarly, the other half open interval as the set of all real numbers x such that a is less than or equal to x and x is strictly less than b, and the open interval a comma b as the set of all extended real numbers x such that a is less than x and x is less than b. In this case, both the inequalities are strict. Okay, so you can see that these are some special types of subsets of the extended real numbers, and each one of them depends on two extended real numbers a and b, and these numbers have names. In each of these intervals, a is called the left end point. A is called the left end point and B is called the right end point. That it makes sense. Okay, that's a natural name. And these points have other names also. Sometimes A is called the left boundary point and B is called the right boundary point. And in fact, there is a notion of the boundary of a set. Okay, we will come across those things, but right now let's complete this. And B is called the right end point. And after this definition, immediately there is a remark about notation. And the remark roughly says this: there is no point writing things, okay. The remark says this. Well, is this really the remark after this multiple meaning? Yeah, yes. Say you have this interval, right, 2, 3, where the left end point 2 and the right end point 3 actually in this case are real numbers. They could have been plus or minus infinity, each one of them. Okay, but we have chosen 2 and 3. Say, let's see this itself. Now this symbol 2 comma 3 has unfortunately 2 meanings now. One of them is of course the interval, the set of all extended real numbers x such that these inequalities are true. But there is another meaning also. It is that this is an ordered pair of 2 real numbers. Those real numbers are 2 and 3. That is, this is an element of this Cartesian product. Now, there is of course, if just simply this symbol is given and nothing else is said, there is no way of deciding whether it has this meaning or this meaning. But usually such is never the case, right? Usually when you have such a symbol, it appears in a context, and from the context itself you will be able to figure out what the intended meaning is. To avoid this confusion, some authors use different way of writing this, specifically this. In place of this, some authors write this alternate notation. That is, the square brackets are made to face outwards. Okay. This usage, however, is somewhat old, and I don't think many authors would use this. This is in more common use right now. Although it may become confusing, but in practice, no confusion can arise from which you cannot. You cannot circumvent a confusion because of this notation being the same, having 2 different meanings. That never happens, okay, in practice. So that's why there is in fact no need for this, and we will continue to use this. Okay, now next there is an example. What this example says is, you may have noticed one thing. I have written R star here, but from your prior knowledge of these things, there is no way that you haven't seen these things before. Okay, maybe not R star, but interval is something that you already are familiar with from calculus. So that's why it is, you may be thinking, can we not write just R here? And yes, we can, and in fact that's what we are going to write in this example. If the endpoints A and B are in fact real numbers, that is, if they are finite, then the intervals all of them, or all 4 of them, are subsets of R. And you can almost immediately see why. Because the finiteness of A and B prevents the elements in each of these intervals from becoming infinite. Each element has to be greater than or equal to A and less than or equal to B. And since A and B are real numbers, that is, since they are finite extended real numbers, so each element must itself be finite in all of these 4 sets. Are subsets of R. For instance, say this interval, yeah, we can give any example, but let's see what the author has given. Now in place of r star, you can just simply write r. And the reason is that this x can neither be plus infinity nor minus infinity due to these inequalities and due to 2 and 3 being finite. That's why there is no need to write r star. Actually that set r star, this set where you have r star here becomes equal to this set, yet that reduces to this set because of this finiteness. And there are some other types of intervals also. If we really take into account plus and minus infinity, that is if one of the endpoints is infinite, then we have the positive real axis. Although it sounds geometric, but this term has been used by the author, the positive real axis, which is this interval. Note that although the right endpoint is infinite here, but since we have an open interval, so the elements here must be strictly less than plus infinity, and at the same time being greater than or equal to 0, all the elements themselves are real numbers in this interval, although the right endpoint is not a real number. So we can write here, because of that fact, r and not r star. Okay, if you want you can write, but ultimately this is the thing. And there is in fact no need to write less than plus infinity. That is implied by x coming from r. Okay, so if you are writing r star here, then you have to write the inequality here. But if you are writing r here, then that's just it. The non-negative real axis Now that we have seen this in detail, we can just simply write this like this without bothering about that other endpoint. The negative real axis, which consists of all the real numbers less than 0, and the non-positive real axis, which consists of all real numbers less than or equal to 0. You have to carefully see which of these axes that we are mentioning are open intervals and which are half open intervals. Okay, this one for example is open. Here also we are not bothered to write that x is strictly greater than minus infinity. That is taken care of by x coming from R, and the non-positive real axis. Note carefully that in all of these four axes that we have written here, nowhere do we have a square bracket on the side of the infinite symbol. Okay, here also, I mean, we have square bracket, but not on that side of the symbol that is not a real number. Here also we have round bracket on this side. Here also we have round bracket on this side, and here also. And that is why these sets, these intervals, after all, are again subsets of R, in spite of having these infinite endpoints. Note that the set of real numbers itself can be thought of as an interval, this open interval. Why? That's because any real number is strictly greater than minus infinity and strictly less than plus infinity. And any extended real number satisfying those inequalities must be a real number. That's why we have this equality. And the extended real number system, that entire set itself is a closed interval. So in this case we do have the square brackets, okay, because any extended real number is greater than or equal to minus infinity and less than or equal to plus infinity. The possibility of x being equal to one of these things is there, okay. Now there are some names given to these intervals depending on whether they have these infinite endpoints. We sometimes refer to an interval having one infinite endpoint as half infinite, a half infinite interval. When you use that term, it should be understood that the interval in question has one endpoint which is not a real number. It can be plus infinity, it can be minus infinity, and the other endpoint is a real number. As half infinite. If both the endpoints are infinite, then the interval is called doubly infinite. Okay. Any other interval, that means any interval other than these types in which both the endpoints are real numbers, is called a bounded interval. So for example, these two intervals, these are after all themselves intervals, right? They are doubly infinite, and the four axes that we mentioned previously, they are half infinite, whereas that 2, 3 or any such other interval is a bounded interval. Next, there is another example. And this example, in fact, is it could have been given as a remark also, but anyway. If A, okay, so now we come to another aspect of these sets. See, the thing is that we see four intervals, right? This, and the open interval. Now, depending on how A is related to B with the order relation, you can decide whether the interval will be empty or not. Okay, and some other things. So, for example, let's take the definition of this first one, this closed interval. What is this? This interval is the set of all extended real numbers such that A is less than or equal to x and x is less than or equal to b. But if this interval is non-empty, suppose this interval is that means there is at least one such x such that A is less than or equal to x and x is less than or equal to b. Now, since order relation is transitive, that would mean that A must be less than or equal to B. But if that does not happen, if A is strictly greater than B, then automatically this cannot be non-empty, it has to be empty. And a similar thing can also be said about these other things. So this example involves that fact. So the example says this: if A is greater than B, then all of these intervals equal the empty set. Okay, there cannot possibly be anything in them. No extended real number as an element. Also, if there is another possibility, right? If A is equal to B, if A is equal to B, then only the closed interval is non-empty, and it turns out that it's the singleton set consisting of A, which is also B, and the other intervals, the half open intervals and the open interval remain empty. Okay, so these two cases are going to be ignored by us because they do not give us any interesting subset. I mean, intervals fine, the definition allows these possibilities, but they are highly boring and almost useless. And that's why these intervals are called degenerate intervals. The other intervals are called non-degenerate, and we will mainly focus on non-degenerate intervals. And degenerate intervals, even if they arise, we will just simply discard them. Okay, nothing essentially will change. And let me just use some more ink before I say something else. Now, using intervals, we will have some other sets. We won't have simply just intervals as domains of the functions that we are going to study, but some other sets also that can be formed using intervals. For example, we may consider this. Just simply saying, okay, the union of these two intervals, one of which is a closed interval and the other one is an open interval. Or we may consider this intersection. It becomes the set of all rational numbers greater than or equal to -1 and less than or equal to 1. Okay, so such things will be considered. These ideas are slowly taking us towards some notions which are topological in nature. What topology is will be discussed, okay, in this book itself, but we are still far away from it. When the time comes, we will see and we will recall these things. Then, at that time, in a much more general setting. Before getting to topology and topological spaces, we will also have to see the notion of metric spaces, which itself is a generalization of the things that we will study here. Okay, so let us now see the next definition. It's about a point being close to a set. Okay, we have already seen when two real numbers are close to each other. You recall the things that we saw in sequences. We invented some terminologies, right? Like epsilon close, epsilon steady for sequences of rational numbers. Such things, if you recall, say x and y are two real numbers, right? Let's recall that we say that x and y are epsilon close to each other, or x is epsilon close to y, when the distance between them does not exceed epsilon, and where epsilon of course is some positive real number. Now, using this notion, we are going to see the next definition, which is epsilon adherent points. Epsilon adherent points. Let X be a subset of the set of real numbers. Now, this X need not be an interval. Okay, we are not talking about intervals anymore. Intervals will come again. But now let us consider any subset X of R. Let epsilon be a positive real number and let X be a real number. We say that X is epsilon adherent. Adherent means to adhere to something, okay, to be close to something, to stick to something. X is epsilon adherent to the set X if there exists a point in the set X that is epsilon close to small x. Such that X is epsilon close to y. Okay, a pretty natural definition. There is a remark after this definition. Similar remarks have appeared elsewhere also before, where we defined some things. The terminology epsilon adherent is not a standard one. You won't likely find this term in any other book. It's because the author has invented this term just so that some definitions can be divided into chunks that are easier to understand, and once you understand those chunks, you can then put the things together, pieces together, and have the full understanding. We have done similar things when we were studying sequences, right? First we defined epsilon closeness, then we defined eventual epsilon closeness, and then we defined the limit of a sequence. It's like that. Is not standard. And we will get rid of it once we have the notion of an adherent part, which is standard. But before that, let's see this example. The point 1.1 is 0.5 adherent to the interval 0, 1. So the set X here is this open interval 0, 1, and the point small x here is 1.1, and epsilon is 0.5. And this is because you have 0.9, this element in this interval, such that the distance between 1.1 and 0.9 is less than or equal to 0.5. Note that you cannot take 1 here. 1 is not an element of this open interval, because the open interval by definition consists of all real numbers x that are strictly greater than 0 and strictly less than 1. So 1 cannot be chosen. However, we can of course choose 0.9, which is an element of this interval that is close to 1.1, and the distance is less than or equal to 0.5. So that's why 1.1 is 0.5 adherent to this set. Similarly, 1.1 is 0.5 adherent to this finite set. There is no need for x to be infinite, it can be finite also. And in this case, you can, however, choose 1. There is this one element 1 in this set whose distance from 1.1 is 0.1, which is less than or equal to 0.5. So 1.1 is 0.5 adherent to this set. And there is one more thing. The real number 1 is also 0.5 adherent to this set. And in this case, you can just conveniently choose 1 itself from the set, because the distance from 1 to 1 is 0, and 0 is of course less than or equal to point. It's in fact less than 0.5. Okay. And now finally we come to the definition of an adherent point. And luckily things are such that I can just simply modify this. Adherent points. Again, let X be a subset of R, and we don't need this epsilon now. I mean, at least we don't need it here in the hypothesis. And X be a real number. We say that X is an adherent point of capital X if X is epsilon adherent to capital X for every positive real number epsilon. If X is epsilon adherent to X for every epsilon greater than 0. And let's just write what that means also, okay, without using this epsilon adherent thing. That is, X is an adherent point of X if and only if for every real number epsilon positive there exists an element y in X such that X and Y are epsilon close. And this does not, it does not, what I am trying to say here is that it does not matter how small epsilon is. Oh, I wanted to phrase that in terms of Y, so I got confused. It really does not matter how small you choose epsilon to be, say something like this, unimaginably small. Even then, if you are able to find a Y in X that is close to X in such a way that the distance between them is less than or equal to even that small epsilon, and if this keeps happening, no matter what your epsilon is, large or small, anything, as long as epsilon is positive, then we say that X is an adherent point of X. So you can imagine that if your set X is this, then that small x is extremely close to X. But even then, note that we are not saying anywhere that X has to be an element of X. That is not necessary, and the examples that are coming next will make it clear why. Without a small x being an element of X, also it can be an adherent point. This will be 9, item number 919, and this is one such example. The number 1 is an adherent point of the open interval 0, 1. Okay. Why though? Can you see why? Instead of doing algebra, let's see what this means geometrically. You just imagine the numbered line, and to show things clearly, let's just mark out 0 and 1 fairly far apart. So what we are saying is that this real number 1 is an adherent point of this set. What is this set, by the way? In this diagram, it is the set of all real numbers that correspond to points that lie to the right of 0 but to the left of 1. To the left of 1, it does not matter how close that is to 1, but if it lies to the left of 1, then it will be an element of this set. Now say you choose your epsilon very small. Say you choose this much to be epsilon. Suppose this distance is epsilon. Okay, then correspondingly on either side of 1 you have these lines marked out that represents this distance. This much distance is epsilon, these distances are larger than epsilon, and the ones smaller than epsilon are like this. And what you want an element of this set, this interval, that should be so close to 1 that the distance between that element and 1 should be less than epsilon. This much is also epsilon, right? So your interval, your set is this. So in this region, if you choose something, then obviously that distance from 1, its distance from 1 will be less than epsilon. So it does not matter how small you choose epsilon to be, since there always will be something even closer to 1 from the left hand side of 1 than that distance. That's why you will continue to have points from this set that is closer and closer and closer to 1, always beating that epsilon distance. And that's why 1 is an adherent point of 0, 1. You can of course show this analytically, algebraically, but I am not going to do that. The understanding is more important right now. Note that (0.5), this real number, is also an adherent point of 0, 1. The 0.5 number is of course this. It lies in the middle of this interval, and it is an adherent point because in this case, as an element, it does not matter what epsilon you choose. So the epsilon that now you will choose will determine a small region around 0.5, just like here it determined a small region around 1. So here you get a small region around 0.5. Now the slight problem that you were having with 1 of choosing an element that can be closer to 1 than epsilon, here you do not even have that problem. Every time, no matter what epsilon is, the element that you can choose from this set is 0.5 itself. So the distance of 0.5 from itself is 0, and that always beats epsilon. So that's why 0.5 is also an adherent point. And do you see one point here in this whole thing, that in fact this is not a special property of 0.5. It is true for any element of the set itself. In other words, every element of a set is its adherent point in a trivial way, because regardless of what epsilon you choose, you can always choose that element from the set itself. So its distance from itself is 0, and 0 is always less than epsilon. So you get the result almost. I hope you understood that in fact if you are given a set X, any subset of R, then every element of X is an adherent point of X. But here you see one example of a point which is not an element of this set, and still it's an adherent point. Okay. But points which clearly are somewhat far away from the set in a vague sense, I mean, for example, if you think of 2, 2 cannot be an adherent point of this set. That's because you can choose a region around 2 sufficiently small so that there is no possibility of that region intersecting the given set. So you cannot choose such a point which will lie in that region, which will be closer to the point 2 than your epsilon. Okay. So that is why also two is not an adherent point. Of 0, 1. That is, simply, very loosely speaking, you think of the set on the real line geometrically, and you see which points are sticking to the set. 1 sticks to the set from the right side, although it's not an element of the set. So does 0 from the left side, but any other points do not really stick to the set. And the points that are inside the set, of course, stick to the set. So those are the adherent points. And based on the definition of an adherent point, now we are going to make a next definition. Because we are saying so much about adherent points, it is an important concept, likely you may be thinking, and yes, it is. So it would be helpful if we name the set of all adherent points of a set something, and that thing is called the closure of a set. Let X be any subset of R. The closure of X sometimes denoted by this symbol X bar, and sometimes it's also written as CL of X, closure of X. Okay, here however we are going to use X bar is defined to be the set of all adherent points of X. For example, in the closure of 0, 1, this open interval, we have 0, we have 1, and we also have all the elements in the set itself, because those are adherent points. I just simply remarked that no point outside of all these points is an adherent point. However, all these things are simply just, I have just said, okay, we haven't proved. So if our remarks about this set and its adherent points are correct, then the closure of this open interval is actually the closed interval. That's because the elements of the open interval are all the real numbers strictly lying between 0 and 1. They are adherent points of this open interval, and additionally we also have the adherent points 0 and 1. And if no other point is an adherent point, then this is the set of all adherent points, in other words the closure. Okay, we will see these things. But now, before we end the video, let's just mention a lemma which lays out the basic properties of closures of sets. And the very first property tells us about this observation that we have made about adherent points, that any element of a set is also its adherent point. That is the first property, and there are others also. So this is lemma (9.1.11). Elementary properties of closures of sets. Let x and y be arbitrary subsets of the set of real numbers. Then the first property is that x is a subset of the closure of x, which states our observation formally that every point of a set is also its adherent point, and hence it belongs to the closure. Next, the closure of the union of x and y equals the union of their closures, and the closure of the intersection of x and y, this however is not equal to that other thing, but is contained in the intersection of the closures of x and y. There is another one. If x is a subset of y, then the closures of these sets are also in that relation. Then the closure of x is a subset of the closure of y. And we will prove this in the second exercise of this section. That is, in place of proof, we have been asked to see exercise 9.2. And let me just end the video here itself. We will continue from this point in the next analysis update. But before I go, let me just say one thing. There is a general advice while dealing with these things, and that is that whenever possible, you draw a diagram. You have seen that the notion of adherent point, if you I mean, it's very easy to make mistakes and get confused. However, if you draw a figure of the set somehow, it may not be a very accurate or an actual representation of the set itself, but at least if you draw some sort of figure, if you are able to do so, then many things you will almost immediately see there on the page, on the paper itself, or on the board. That's a general advice. So that's just it for tonight. So see you in our next update. When is that? This coming Tuesday itself. And okay, so we have again, what are the things we have done again recently? Group theory from Herstein, field from Herstein. So let's do vector spaces this Tuesday. So see you on Tuesday with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.